Hey everyone, in this video walkthrough we'll be going over the best and worst case runtime of Tricky. And this is problem 4 on the exam prep worksheet for asymptotics and bits. And this is one of the first videos I've actually recorded this semester. I'm not pulling content from past semesters, so hope you all enjoy. But the idea here is that we're trying to find the runtime of this function Tricky. And when we're looking at Tricky, it's a tricky function given the name, right? So what I recommend is that when we approach this problem, don't be discouraged if it makes zero sense immediately. This made no sense to me when I first saw this problem. How we want to approach this is that we want to try to understand some idea of what's happening in this code, right? Then let's try to understand how is binary kind of playing into this, and then we'll try to generalize what we learned from an example to a best and worst case runtime. Okay, so if that made no sense, no worries. Let's dive into this problem, and I'll be approaching it as I'm a student on an exam. Okay, so the first thing I'm kind of noticing here is that in Tricky, we have a recursive skeleton, right? We have some recursive call here, and we have some if condition. Okay, so we're going to keep executing this recursive call until the input n that's passed in is less than or equal to 0, right? This is when we stop recursing, okay? So since we're dealing in asymptotics, we're going to assume that n is really, really big in the positive direction. So when I'm looking at the n that's passed in, we can kind of make this condition a bit more concrete, and we can say when n is equal to 0, then we're going to stop. So with this in mind, let's just walk through an example and see what's happening here. Okay, so I'm going to create this little table. And in my table, I'm going to say we have a function call, and then we have our input, n, okay? So the function call is going to keep track of like which function call is it? Is it the first, second, third, or fourth? So the first time I call my function, my input is going to be, let's just choose a random input, 1, 0, 1, 1, 0, 1. And this number is in binary. So if binary is a bit confusing to you, I recommend pausing my explanation, watching a video on how numbers in binary are represented, and then coming back. Because it's definitely important to have some idea of how numbers are represented in binary. I'll link a helpful description, a helpful video in the description. So anyways, coming to this example, when I have the input 1, 0, 1, 1, 0, 1, let's see what happens when I do the AND operation with n minus 1, right? So let's see here. If I have 1, 0, 1, 1, 0, 1, and this is my n, and I'm doing the AND operation with n minus 1, well, what is n minus 1, right? So this number in binary is 1 plus 4 plus 8 plus 32, right? So this number in decimal is actually going to be 44, 45. And how I got that this number is 45 is that we have a 1 in the 1 spot, there's a 0 in the 2 spot, there's a 1 in the 4 spot, a 1 in the 8 spot, a 0 in the 16 spot, and a 1 in the 32 spot. So every place there's a 1, I'm taking these spots and I'm adding them up, right? Okay, so TLDR, the number is 45 in decimal. Okay, so if I'm looking at n minus 1, right, n minus 1 is going to be 44 in decimal, right? Which means I can get to 44 by doing let's look at this. I can do 32 plus, I can't do 16, I can do 8, plus 4, plus, that's it, right? So if I'm looking at that number in binary, it's going to be 1, 0, 1, 1, 0, 0, right? And this is corresponding to n minus 1, okay? So now that we have n, now that we have n minus 1, let's do the AND operation and see what results, right? So after doing this AND operation, we're going to get 1, 0, 1, 1, 0, 0, right? And it happened to be the same as n minus 1 in this example, the number that we got out, but I'm not sure if that's always going to be the case. Regardless, let's do one more iteration before we try to draw any conclusions here. Okay, so the next iteration, we have the input, which came from over here. Oh, shoot, wrong color. And the input is going to be 1, 0, 1, 1, 0, 0. Okay, so taking this input now, we can do the same and with n minus 1. So I have 1, 0, 1, 1, 0, 1, and this is my new n. So now let's take a look at what n minus 1 is going to be. Oh, shoot. It should be. Okay, so let's look at what n minus 1 is going to be. Well, this number in binary is 32 plus 8 plus 4, right? Which is 44, okay? So if I look at n minus 1, right, we want my n minus 1 to be here. If I'm looking at the n minus 1, it should be equal to 43. And I can get 43 by doing 32 plus 8 plus 2 plus 1. And what I really want to highlight here is that the only difference between 44 and 43 are the 4 and the 2 plus 1 here, right? Otherwise, it kind of has that same sum. Well, let's see how that translates when we're looking at these numbers in binary on top of each other. So I have 1, 0, 1, right? Because that's the 32 and 8, and we don't have anything in the 16 spot. And now what's going to happen is that I have nothing in the 4 spot, and then I have a 2 and a 1. So what's kind of cool here is that the number n and the number, n minus 1, they are exactly the same up till this line right here. At this point, we can see that the remaining bits in n are flipped in n minus 1, right? Well, that seems to be kind of like a cool observation, but we don't really know if it's always the case. So let's try moving on to the next iteration here. So when I do this AND, I'm going to see that these numbers, these ones stay, but if we're looking at all of these remaining bits, they're flipped above, so we put zeros here. Okay, so now we can kind of fill in our table. So in our table, we'll say 1, 0. And we're about to make some really cool conclusions very, very soon, but let's just hold tight and do one more iteration, just so we can kind of be sure of these conclusions. Okay, so all I've really done is I've taken this number we got, put it in this table, and now let's look at the next iteration of this algorithm. Okay, so the next time around, we have 1, 0, 1, 0, 0, 0, which is our n. And this number is a different number, actually, than what we've seen so far. And this number is going to be 32 plus 8, right, which is 40. Okay? So now let's look at what our -1 is going to be, right? N minus 1, that is. So I'm going to try to figure out what is this n minus 1 here. Well, it's going to be 39, right? Which is equal to 32 plus 7 plus, oh, just kidding. We can't really do 7. I want to write it in terms of like powers of 2. So it's going to be equal to 32 plus 4 plus 2 plus 1. And now what we can kind of see is that when we're comparing these two numbers, right, if I'm comparing 39 to 40, notice that they're exactly the same, except in 39 we have these ones here, except in 40 we have this 8 here. And what that kind of looks like when we're looking at these binary representations is that this part of the number for n is a 1 in the 8 spot and zeros in the 4, 2, and 1 spot, right? But if I'm looking at n minus 1, we have a 0 in the 8 spot, and we have 1s in the 4, 2, and 1 spots, right? And what we'll kind of notice is that if I'm looking at this number and I split it in half, not necessarily in half, but in two sides, notice that n and n minus 1 are identical on the left half of this green line. But if I'm looking at the right half of this dark green line, notice that n and n minus 1 are flipped, right? And now what's going to happen when I do this AND operation here, it becomes a bunch of zeros and 1, 1, right? So now what we can do is we can put this back in our table. So this is the fourth iteration of our algorithm. Okay, so now let's just do the last iteration, and then we'll start drawing some cool conclusions and generalizing from there, right? So for this last iteration, we are going to once more look at an AND operation. So now we have this should be 32. And if I'm looking at -1, it's 31, right? This is n. And if I'm looking at n minus 1, it's going to be 31, which is a 0 in the 32 spot, and it's going to be 1s everywhere else. Okay, so now what's really kind of cool here is when I do this final AND operation, notice that all the bits become 0, right? Because when we're looking at our kind of example or idea that we're kind of continuing, when I look at both halves of these number, notice that these ones are all different, and we can actually just draw the green line right here, right? Both of these numbers are completely flipped now, right? So what we'll see is that the fifth time around, our input becomes 0. And now let's draw some really cool conclusions. Now that we've walked through this really, really thorough process of this thorough example, let's draw some cool conclusions. So the first one I'm going to draw is that every function call, our input loses a 1. Okay, so let's see why this is the case. Just based on observation, notice that we have 4 1s in the beginning, then we have 3 1s, then 2 1s, then 1 1, and then no 1s, right? So we can see here that every function call we're losing a 1. Well, why is that the case? Well, the reason it's the case is that looking at an arbitrary function call, let's look at this number right here. If I'm looking at this AND operation that we're doing, when I have this number here, and if I'm looking at n minus 1, right, what ends up happening is that we lose this 1. The reason we lose the rightmost 1, and this is always going to be the case when I and n minus 1, is that n minus 1 in these last 4 bits are going to be flipped of these last 4 bits, right? Because in n, I have an 8 here, so in n minus 1, I should have a 7 in these last 4 bits, right? Because these two numbers are identical up till this point. So after this point, in order for the sums to be n and n minus 1, there needs to be a 7 here. So what we'll see is that n minus 1 is always going to have 1s in all of n's trailing zeros. And for n's rightmost 1, it'll have a 0 there. And because of that, when we and n minus 1, we'll basically get rid of this 1. Okay? Okay, so the next observation we can make here is that the number of recursive calls is equal, or let's say proportional, to the number of ones in n, right? Notice here that in the n that I'm given, we have 4 ones. And accordingly, we have 4 recursive calls right after the initial function call. So what we can kind of see is that this naturally lends itself to a best case and a worst case possibility. So at this point, pause the video. With all of this in mind, what is the best and worst case? So yeah, pause. Okay, coming back, looking at the best and worst case, just the possibilities, like what they are. When we're looking at the best case here, it's the possibility or the situation when we have as few zeros, or my bad, we have as few ones as possible. And when we're looking at the best, or when we're looking at the worst case here, it's kind of the opposite. It's when we have as many ones as possible, right? That's the difference here. In the best case, we have as few ones as possible so that we don't do many recursive calls. In the worst case, we have as many ones as possible, so we do many recursive calls, right? So looking at examples of the best and worst case inputs, just like arbitrary, in the best case, I'll have some number that has 1, 1 in the very beginning and then zeros elsewhere, right? And the reason it needs to have at least 1, 1, because if it doesn't have a 1, it's the number 0, right? And the number 0 isn't really defined asymptotically, okay? So when we're looking at this input right here, notice that n minus 1 is going to be, right? This is n minus 1. So when I add the two numbers, I get a bunch of zeros, right? So when this specific input is given, right, what's going to happen is that the first time I do n and n minus 1, when I enter the next recursive call, we'll see n is equal to 0 and we'll stop. So our best case is going to be theta of 1 because I'm only doing like one additional recursive call no matter what n is, right? So we can think about the runtime in the best case as constant. right? As n gets really, really big, notice that I'm always just doing one recursive call. I'm always doing the same amount of work. That's the definition of constant runtime. Okay, so looking at the worst case runtime here, it's the situation when we have as many ones as possible. So let's say we have a ton of ones. We'll still have to have a leading zero, so it's positive, but we're not going to delve too much into that for now. So we have a ton of ones here, right? And notice that every time I call my function, right, by this point right here, we lose a one, right? More specifically, we lose the rightmost one. But regardless of which one we lose, if I'm looking at all of the function calls needed to eventually get to 0, notice that the total number of function calls is going to be equal to the number of ones. Well, how many ones are in a number n, right? So this is actually like a pretty tricky question. How many ones are here with respect to n? Like if I say that this is n, how many ones are there? So the answer is that there's actually going to be log n ones, right? And the reason that there's log n ones is that if I have some number n, let's assume that if I'm looking at its binary representation, it takes log n bits to encode the number n in binary. That's just the definition of how binary works, right? So if all of these bits are ones, then there's log n ones. Okay, just kind of saying that again. When we have some number n, and I'm encoding n in binary, it takes us log n bits, right? So if it's the case that all of these log n bits are 1, right, then we'll see that the total number of function calls we do is going to be log n, and our final runtime in the worst case is going to be theta of log n. Okay, so yeah, so that's our final runtime here. It's going to be theta of 1 and theta of log n. I hope you all enjoyed this video, and yeah, have a good rest of your guys' day. Go Bears.